couldn't get nearly enough. It took 2 lessons, and I'll leave one light on. It's a little overwhelming. However, I expect you to actually understand some of it. Your homework equation, your homework tonight is on this, and there is a bonus problem on the homework for 20 points. That's 20 raw score points. That raises your grade by 2 points overall. So if you have an 88, you have a 90. No one has ever gotten a bonus. It is difficult to do. It is doable. One person came very close one time, back in 2011. But since then, no one has really come close. So if you want a challenge, do the bonus. It is a very challenging problem.
Extra, like, is there partial credit on the bonus?
I will give partial credit, but only up to the point where you don't do it right. Okay? Welcome back, everyone. All right, now we're doing the convection equations. All right, so let's get going. You have in front of you the handout that on the supplemental reading, which I suggested you take a look at, is very important. Okay. How many of you are in fluids or have fluids? Good. All right, you'll recognize that there's a great deal of similarities between this and Navier-Stokes. So, as a matter of fact, the Navier-Stokes is really embedded in this presentation. So, with that, let's see if this works. Okay. The first equation we're going to take a look at today is the first of, you're going to see these equations again and again and again. There's the conservation of mass equation. The equation numbers here reference the supplemental reading for chapter 6. And what this basically says is that the net change of mass flow in the x direction plus the net change of mass flow in the y direction must be equal to 0. Okay? Mass is neither created nor destroyed. Okay? And I'll occasionally give you a reference in the supplemental material if you printed it out. This is figure 6.1. All right, now if we assume for a moment that the fluid density is constant, then the conservation of mass becomes an even simpler equation. That is the partial of u with respect to x plus the partial of v with respect to y is equal to 0. Let me point out for a moment that u is the velocity in the x direction, v is the velocity in the y direction. Large V is equal to, large V squared is equal to u squared plus v squared. Okay? All of these derivations are in 2 dimensions, not 3, although they can be done in 3 dimensions. Here's Newton's law of motion. And what we do here in Newton's law of motion is we break it down into parts before we get into conservation of momentum. And the first part is the surface forces in the x direction, given in equation S3. The first term represents the normal stress in the x direction. Yes? I have plenty of those. Just need to be here on time. They're floating around. Go look for them. The next is net change in the fluid static pressure in the x direction. And then the last is the net change in the shear stress in the x direction. So we have normal stress, the fluid static pressure in the x direction, and the shear stress in the x direction. We have the same term for the surface forces in the y direction. Now, the conservation of momentum then in the x direction is on the left side is the x momentum of the fluid leaving the control volume in the x direction, and the net change in the x momentum of the fluid leaving the control volume in the y direction. Then we have the change of the normal viscous stresses in the x direction, change of the static pressure in the x direction, and then lastly, well not lastly, but then the shear stress changes in the x direction, and lastly the body force in the x direction. That's the big piece. Okay, then the y direction is identical to that, except with everything with respect to the y direction. Now, this is an interesting equation. This equation is the normal viscous stress. And your author does not go into how it gets there. What's important about this equation is that you have the normal viscous stress as a function of two things. Your velocities, u and v, and your viscosity, your dynamic viscosity. Now, how they got this equation fills about 2 pages in the classic text on the matter by a guy named Schlichting. Schlichting did his work in the early part of the 20th century. He was one of the foremost scientists studying boundary layer theory as a fallout of the flight of airplanes. This is a complicated derivation. We can spend the whole class just looking at the derivation of how he got this. If you want to really see it, it's all in his book. I have his book. It's kind of interesting to look at. But that's the net result. And it allows us to do some interesting things when it comes to the momentum equation. Okay? Similarly, there is another derivation for the shear viscous stress, which is again expressed in terms of the 2 velocity components and the viscosity. So what are we going to do? We're going to take those, and we're going to plop those all into the conservation of momentum equation. What you see here is the momentum in the x and y direction. Okay? And this is for the x direction. And then we have the pressure changes, and then here we have the normal stress, and here we have the shear stress, and down here we have x. Now, if you are attentive, you will notice in your homework that your first homework problem is beginning with equation 6s11, show how, by assuming an incompressible fluid, one can obtain equation 6s13. So you're probably asking yourself, what is 6s? Here's 6s13. See how nice and small that is compared to this? That's what you're starting with? That's what you're getting. Now I'm going to give you a hint. Don't come and ask me any equations on this. I'm not giving anybody any help on this. Because there's only one thing you need to recognize, and then you can do this with a little math. And if I told you the one thing you need to do, it makes the problem very simple. It trivializes. So the question is, can you think about it? And that's only worth 5 points. So if you can't, don't feel too downcast. But you're going to have to figure this one out on your own. Okay? Then show me the steps. Now, on 20, on the bonus, this is the solution for the bonus problem. Okay. Well, that's the first page. This is the second page. Okay? So there's a whole different order of magnitude between problem number 1 and problem number 2. There's a little history on that. Way back when, I don't know, 7, 8, 9 years ago, something like this, I was just doing this class, and I said, and we'll get to the point where we do where the bonus comes in. And I said, why don't you do this for homework? You know, because the author says, if you do this, this, and this, you can get to this. How hard can that be? Well, after about 20 hours worth of work, I finally figured it out. I don't know if it took 20 hours. It took a long time to figure it out because there's some steps in there. Now, I gave you one big hint. The one big hint on the bonus is that you have to recognize that big V squared is equal to small u squared plus small b squared. If you do that, you got a chance. Okay. Anyway, since I had assigned it, I felt obligated to solve it. So I did, and there's been a bonus problem ever since. So. But I'm waiting for someone to get it all the way done. And maybe this class this year will be it. Okay. So anyway, that's part of your homework right there, is to get from 6:11 to 6:13. And it's actually pretty simple. Okay. All right, now we get more interesting. Now we're going to talk about the conservation of energy. But now in the conservation of energy, we're going to take different components. And the first component of the conservation of energy we're going to take is the advection considerations. Now, advection is the heat transfer that occurs associated with the movement of fluid. Okay? And it includes the movement, the kinetic, as well as the internal energy components. This diagram, or this equation, comes from figure 6S5 in your supplemental reading if you printed it out. So, what you have is the internal energy, E, and then your total velocity, which is why it's important to understand that, V squared. And what it is what leaves minus what came in minus what leaves. That's the first two terms after the equal sign equals the bottom term, cancels out. So it's just a change. It's just a differential formulation. You've seen it here half a dozen times, and that's what it is. It's just a little more complex. Here's the conservation of energy, the conduction equation considerations. The conduction term, you're already familiar with the conduction term. That's that term right there. And again, this is the energy associated with the change of conduction in a differential element. What comes in, what leaves, and the difference. I get too many buttons here. Oh, sure. All right, and then the conservation of energy for body forces and surface forces. And you see the X, and you see the shear, the pressure, and the normal stresses that we've already talked about. Then we put the whole thing together, 2 dimensions. And this is based on figure, I don't know if I have it down here. Let's look at the terms for a moment. This term here is your advection term. This is your conduction term. These are your body forces. These are your pressure terms. These are your shear and normal stress terms. And this is your internal energy generation. So, it actually looks a lot like what you've seen in thermo and what you've seen so far. It's got a few extra things in there, some of which we'll ignore. Now, take a look at your homework. What equation are we going to start off with?
This one.
Pardon me? This one. This is where you start. Okay? Now, this is where you end up. Now, it's not as complicated as you think. I'll give you a couple of hints. This is called your viscous dissipation term. And this is what viscous dissipation is. Okay? This is, press the wrong button. This is your viscous dissipation term right here. So what you got to do is, you got to recognize that term is embedded here in this equation. Okay. Plus, you've got to go to, if you have any chance of doing this, you've got to go to the supplemental reading and you've got to read the hints that they give you getting from 618 to 619. Because it's not just a question of doing the math. It's a question about applying the boundary layer similarity, the boundary layer assumptions. And we're going to talk about those now in just a moment. But you have to make some decisions about the boundary layer assumptions. All right, so that's the thermal energy equation in the form that we will typically use. And more often than not, we're going to ignore the viscous dissipation term, and we'll often ignore the heat generation. This is a refined version of the conservation of energy term, where the first two terms here represent the net change in enthalpy, where the internal energy and the flow work terms associated with advection have been combined and now are contained in these two terms for the x and y direction. Here's your conduction, and this is your static pressure, network done by the static pressure forces, your viscous dissipation. And by the way, what is viscous dissipation? It is the net rate at which the kinetic energy is irreversibly converted to thermal energy due to viscous effects. What is that? You've had fluids. What is that? It's the frictional pressure of drops, okay? Associated with a real viscous fluid flowing in a real channel, okay? And then the last is, by the way, if you're thinking, oh my goodness, I'm never going to give you a problem like this on, I'm never going to give you a derivation like this on the test. Okay? But at the same time, if we don't go through this, everything that we're going to do for the next 10, 15 lessons is just waving hands in the air. Okay? You've got to, even though you may not completely grasp this, and you probably won't, because most graduate students don't get this the first time around. At least you have an appreciation that there's some science behind what we're doing. It's not just all waving our hands. So, I'm sure you appreciate that. Okay, now, the dreaded boundary layer assumptions. Okay, well, you've seen this. I drew this on the board. This is the velocity boundary layer. We have the laminar region. We have the transition region. We have the turbulent region. And then out here we have the viscous sublayer, the buffer layer, and then the turbulent region here, where the fluid is very turbulent. You notice the velocity profile here and the velocity profile there. This is a free stream velocity. This is your y direction, your x direction, u, v velocities. And this line right here, that's your v. Okay? That's your v. Pythagorean theorem. Large V squared equals U squared plus V squared. Okay? All right. Critical region. We'll get to that in a couple lessons. All right. Now, these are key to solving the bonus problem. The first boundary layer assumption, but these are all for the velocity boundary layer, is that the velocity in the boundary layer in the u direction, that is along the surface of the plate. And by the way, everything we're doing today, and we'll be doing for a while, is based on flat plate flow. Okay? As a matter of fact, next class, just to give you a little excitement, next class is a Blausius solution. Classic heat transfer derivation called the Blausius solution. Blausius was a PhD student working for Prandtl in Germany, along with Schlichting. A lot of things going on in Germany. And anyway, his dissertation was to solve all these equations, come up with actual value of H in the boundary layer. And lo and behold, he did. It's called the Blausius solution. It's very interesting. So anyway, and he made, these boundary layer assumptions were made by Schlichting, Prandtl, and then Blausius, along with a number of other people. And the reason they're made is because the reason they're used is because they do represent a good estimation of what's going on in the boundary layer. Here, the first one is that the velocity along the plate in the x direction is much, much greater than the velocity normal to the plate. All right, next one. The velocity, u, which is along the plate, the change of u from the surface of the plate where it is 0 up to the end of the boundary layer where it is equal to u infinity is much greater than the change of u as it moves down the plate, or the change of v as it moves up in the boundary layer, or the change of v as it moves down the plate. Okay? So, another boundary layer simplification in the velocity boundary layer is that the change of the static pressure in the y direction is approximately equal to 0. The static pressure force, not to be confused with the static pressure of the weight of the fluid itself. And this is, and so because of this, the change of pressure with respect to y is approximately equal to 0, we can say that we will treat the partial of p with respect to x as just simply the change of p with respect to x, and it tends to be a constant. So what does this? What does that physically mean to us? It physically means that the frictional pressure drop is what?
0 in the x direction?
What?
0 in the x direction?
No, not 0 in the x direction. Constant. Constant. Which goes along with what you see with all the stuff in fluid mechanics. Okay? So, in other words, the frictional forces are constant, given a certain geometry. All right. Now, let's take a look at the boundary, thermal boundary layer. This, of course, should look familiar to you as well. We have our temperature profile. Here's our thermal boundary layer. And the one boundary layer assumption associated with the thermal boundary layer is this, and that is that the temperature change is much greater in the y direction in the boundary layer than as you move down the boundary layer. So, now, we have taken all those assumptions and we apply them to the equations that we have already seen. The equations of momentum, that is, or the equations associated with mass, momentum, and energy. And what you see are 3 equations which appear in your textbook. The first one is equation 615, which is the conservation of mass. Okay? This is assuming a fluid with constant fluid density. The next one is equation 16, which is the conservation of momentum. Okay. And now I want to point out something as well. I'll point it out in a moment. But what do you have here? What are these 3 terms? Well, you have the change of momentum in the x direction. This is for the x. This is the momentum equation for the x direction momentum equation. So you have the change of velocity with respect to x times velocity. You have the change of velocity u with respect to y times the y velocity v. And then this is your pressure term divided by density. And over here is what's left of your viscous, no, this is what's left of your stresses, of all the stresses. And this is constant. All right. Then down here in equation 617, you have the change of temperature with respect to x times u plus v times change of temperature with respect to y plus your diffusion term here, and this is what's left of the viscous dissipation. Not much. And Q dot's not over. So that all these equations have text in your book that talk about all of the assumptions that get to this point. And I can't put them all on the slides because otherwise it'd just be a million words. And I'd rather have a million partial differential equations. Okay? Now, the last part of the presentation, and the most important because it leads us to some results. Boundary layer similarity, the normalized boundary layer equations. Okay, let's look back here for a moment. Does anybody notice anything out there that looks and that might be useful? And I know right now the brain numbness is setting in from 20-some PowerPoint slides full of differential equations.
You can
Come on.
plug 615 into 616, solving for du dx equals negative dv dy, plug it in into equation 16.
These two equations are mathematically almost now similar, okay? They're almost identical. What's not identical about it? Well, you've got the viscous dissipation term. If you ignore that and you ignore the pressure change, you have two equations mathematically that are exactly the same, except for you have up here, you have nu. What did we say? That was the mechanism for momentum diffusion, right? Dissipation. And down here, alpha, which is the mechanism for thermal diffusion. Well, somebody, I'm not sure who, but Glausius recognized this, other people recognized this 100 years ago. They said, this could be useful in solving for these mathematical relationships and getting an answer. And that's what Glausius did. We'll talk about that next time. All right, so that's what boundary layer similarity is all about. The conservation of mass and momentum equations in the x direction may be solved simultaneously. Now, why this is complicated is as follows. I'm going to show you. Okay. This equation right here, the momentum equation, is relatively easy to solve for. Okay? We're going to be able to solve that. But we come down here, and Megan, why is this equation tough to solve?
Gosh, I don't know.
Yes, you do.
I do?
All right, what are we solving
because-
for here? We're solving for u. What are we solving for here?
Temperature?
What do we have up here? U and v, velocities. And that's it. And this. Nu. What do we have down here? T's, alpha, and mathematically, these equations are coupled. All right? In other words, you can't solve the temperature equation unless you know what? Relationships for velocity, u and v. Okay. So velocity as a function of location in the boundary layer may be solved without regard to the temperature field. That's what I'm saying. It's relatively easy to do that. However, the temperature field in the boundary layer cannot be solved without knowledge of the velocity field. In other words, the temperature and the velocity fields are coupled. Mathematically, this causes a lot of head scratching. All right. So the solution. Now, just keep in mind, this is essentially the introduction to what Glausius did. Also, Reynolds, we're working with him too. First of all, neglect that remnant of viscous dissipation. Let's face it. Does the water flowing through a pipe really heat up much? No. No. So we can ignore that pretty safely. Okay, we're going to ignore that. And then you have the following equations. This is your momentum equation, and this is your temperature or energy equation. And the note at the bottom says the advection terms and the diffusion terms are analogous. Okay? Already pointed that out. Now, we're going to introduce some similarity parameters. Get used to this because we're going to do it again and again and again and again and again ad nauseum in this course, okay, in the convection block. All right, these are all dimensionless parameters. X star is equal to X over the length of the flat. Now, we're dealing with flat plates. So X star is going to be X over the length of the flat plate, L. Y star is going to be equal to the distance up normal to the flat plate divided by the length of the flat plate. U star, which is the velocity, the non-dimensionalized velocity in the x direction, is going to be equal to U divided by the total free stream velocity, V. Keep in mind, remember, V is that vector quantity, or it's a scalar value of the vector quantity, to be precise. V star is equal to V divided by big V. T star is equal to the temperature in the free stream minus the temperature of the surface over the temperature of the free stream minus the temperature of the surface. And this P value, P star, is going to be the pressure divided by rho times V squared. L is your characteristic length. For a flat plate, that's the length of the flat plate, and V is the upstream velocity. If we apply the similarity parameters and do the math to the two equations from the preceding slide, we end up with this result. Here you have the momentum terms. You have the pressure and the shear stress terms. And it turns out that this term comes down to here, this comes through, but the nu divided by V over L is the same as 1 over the Reynolds number. Okay? Down here for the energy terms, we end up with this result, and that is 1 over the Reynolds number times the Prandtl number. Now the significance of this is that we now have equations, if it allows us to apply solutions from one surface with a given set of conditions to another surface that is geometrically similar with different conditions, and the Prandtl number is equal to 1. And you'll recall that we ended our discussion of the Prandtl number the other day. All right. And the Prandtl number is equal to what? Who recalls what? Open your book.
Nu
Go
over
to
alpha.
what?
Nu over alpha.
Right. Okay. And you can always check 6-2. All right, now, hold it now, I get jumped too far. All right, now here's where things get a little hairy. And I'm still going to wave my arms a little bit on this stuff because it's just not enough time to try to go into all of the detail. But you can see where the math is going. U star, it turns out, is equal to a function of x star, y star, the Reynolds number, and the change of pressure with respect to x, which is typically constant for a certain geometry. On the other, the change of u with respect to y, evaluated where y is equal to 0, y star is equal to 0, is equal to a function of x star, the Reynolds number, and the pressure constant. The shear stress is equal to mu, the definition for shear stress is equal to mu times the partial of u with respect to y, evaluated where y is equal to 0. Now if we substitute in our similarity parameters, this turns out to be equal to mu times the large velocity, total velocity, free stream velocity, over the characteristic length, times the partial of u with respect to the partial of y star at y star equals 0. If we then recall our definition for the coefficient of friction, it is the shear stress divided by rho v squared over 2, which would then be equal to 2 over the Reynolds number times a function of x star over the Reynolds number. Keep that in mind. Now let's look for a moment at the Nusselt number. We've introduced the Newton number before. It's equal to H over L times K. We know that the temperature, T star, is equal to a function of X star, Y star, the Reynolds number, the Prandtl number, and the pressure constant. Now, this board I did not finish at the last time's class, so let's pause here a moment. Okay. Basically what this says is let's do an energy balance at the wall. All right, we have a flat plate. And we have boundary layer. And we will have some velocity profile. This curve is the partial of u with respect to what? Okay? That curve, which I constantly draw, represents the change of u with respect to y. Okay? All right. We know at this point right here, something interesting happens. Who can tell me what that is?
Fluid zero.
Pardon me?
The fluid velocity is 0.
That's correct. Stagnation level, layer, nothing's moving. Well, what happens there?
Friction?
Well, there is friction, but yeah, that's where it's friction. But that's not the main thing. We're going to ignore friction by now. Conduction turns into convection. The heat comes out of the plate. If we draw the plate thicker, let's draw the plate thicker for a second. All right. May make it a little easier to imagine. All right, we have conduction in the plate. And at that point, it gets to the surface, and it conducts into the stagnation layer, and then what happens to the heat transfer? It's carried away by the fluid. All right, and that's convection. So at this point, the conduction at y equals 0, Q of conduction is equal to the Q of convection. Now that's important. And this, recognition of this, allows us to create what we know as the energy balance at the wall. Now everything we do for the rest of the time is based on this energy balance at the wall. Now why is that? Because what are we looking for in heat transfer?
Temperature change.
Temperature and amount of heat. What are we looking for in the convection block that will allow us to solve for those things? H. Thus far, we've always just given you H. This whole lesson, this whole business, everything about this is all about finding H. Okay, that's what Blausius did. All right, by the way, it was a constant. How about that? PhD, all that work, and it turned out to be a constant. Well, anyway, he did it. He got his PhD, went on to good things. So, this energy balance at the wall is a big deal. So, let's write the energy balance at the wall. We have conduction coming in, and I'm writing it in terms of the flux. So, Q at the surface, the flux, has got to be equal to minus Kf. Now we're doing the K of the fluid because we're talking about into the stagnation layer. Okay? And then the Q convection. This will be conduction. convection of the surface, will be equal to H times the T of the surface minus T infinity. Okay. We're going to equate these two. And what we end up with is the following result. If we equate these, we can solve for H, and H then is equal to minus K sub F times the partial of T with respect to Y, evaluated at Y equals 0 over Ts minus T infinity. So what does this tell us? It tells us if we can solve for the temperature profile, evaluated at Y equals 0, know the fluid property, conductivity, and the two temperatures, we can solve for H. That's a big deal. Okay? That's a big deal. That's the energy balance integral. Okay, trying to conclude our discussion here. So that's what this says right here. This is your energy balance at the wall. So if we then substitute in these terms in terms of our similarity parameters, we end up with this result right here. Uncharacteristically, he puts in everything. And then over here, the Nusselt number then can be expressed in terms of the function of x star, the Reynolds number, and the Prandtl number, as you can see here down here. Now, conclude today's class with this thought. This is the fellow from whom the Reynolds number is named. This is known as the Reynolds analogy. And Reynolds was doing all the similarity stuff. He was English at the same time as Schlichting and Prandtl and Glausius were working. Came up with this result. He said for Prandtl number approximately equal to 1, which is most gases, are close to 1, and a small or almost insignificant pressure drop along the x direction as for a flat plate, then, here we go. Then you can write the momentum equation in this direction and the energy equation in this. They have the same form and boundary conditions because of their non-dimensionality. Therefore, you can relate the coefficient of friction and the Nusselt number in this fashion, and this is his result. And this is called the Reynolds analogy. And that is, for a flat plate flow, the Nusselt number is equal to the coefficient of friction times the Reynolds number divided by 2. This number is known as the Stanton number, and it is equal to the Nusselt number over the Reynolds number times the Prandtl number, or simply the Stanton number is equal to the coefficient of friction over 2 for Prandtl number equal to 1, as you can see. And this is the what they know as the Chilton-Colborn equation, which is an improvement on the Reynolds analogy for a greater range of Prandtl numbers. So now for a range of Prandtl numbers between 0.6 and 60, which takes up essentially all gases and liquids other than metals, you can relate the coefficient of friction to the Stanton number and the Prandtl number. And that's what Chilton-Colborn did. All right. And I got a minute to spare. Are there any questions? Of course not. Totally. Now you see why I do this on a PowerPoint. Because you can't do this. I'd take a whole week and I still wouldn't get done. I have writer's cramp.